And I guess I'm live. I just thought I'd make this impromptu video because I was watching BlueMarbleScience's live stream last night, and he was reviewing Bev's video that he was making regarding measured angles and so on and so forth. And I thought I was going to investigate what kind of angle would be required on a heliocentric model. So just to recap, Bev was thinking that if the star's up here and your eye level is at the green line, for example, and you measure down, you've got your dip angle here. So I didn't finish this diagram, so I'm just going to add that right about now. So let's say this, I'm going to make it gray. So let's say this gray line is your horizontal. So the angle between the gray and this one here would be the dip angle. And then you would measure this entire angle. You would subtract this dip angle to get the angle above your horizontal. But he was thinking that if you move up, yes, you would have a greater dip angle like this, but somehow he would think that you would have a slightly less angle above your horizontal. And I was thinking, what kind of precision would be required on a heliocentric model? Here's what it is. I tried to create a circle here, and the app that I'm using on this crashed a couple of times. So unfortunately, I'm just going to have to leave it like that. And I just kind of hand drew this. But so if you're down over here, you can see as you can see this far to the ground, you've got your same kind of dip angle here. And then you've got your measurement above your horizontal. And then if you go up slightly and you do the same thing, we predict that you can see a little bit further. You're going to have a slightly greater dip angle, but that since these are for the most part parallel, that the elevation angle is going to be the same. So I was kind of thinking last night about maybe making my own project that would be a standalone calculator app that you could have on your desktop, for example, that would use high precision math libraries. And before I do that, I wanted to see what would be involved. And there are applications out there, online applications. I did a little bit of research already that lets you do that. And in particular, I found this high precision calculator. So I thought I would just go through the math. And let's say that this is going to be maybe 40 degrees. And if I believe yes, I already selected this real degrees. Okay, so let's say you've got sine 40. Okay, so before I do that, let me just do one more quick illustration to kind of give an idea of what I'm thinking of. So if the Earth is over here and you are looking at a star that's up here, you've got be like that there. So your horizontal is kind of like that. So this would be essentially kind of like a standard right angle triangle. So if this is going to be 40 degrees here, I want to calculate the distance from here to here and the distance from there to there. Procyon has a distance of 11.46 light years. I already did a little bit of research. There are 9.46 times 10 to the 12th kilometers per light year, 11.46. So the distance is going to be 108, and that many zeros kilometers away to Procyon. So that being the case, sine 40 times oops, is going to be digits. No, how many decimals do I want? Now let's go with 62. Let's try that again. Okay, so that's going to be my sine. That's going to be along the y-axis. Oops, wrong one. I think I did a Mac control copy. Nope, hang on. Ah, come on. How does this work? I'm used to the Mac. It doesn't even like that. How about yeah, okay, I have to do it that way. All right, that would be the y-axis, and of course I'm just going to copy while I'm at it. I'm going to copy the formula, and then the x-axis is going to be, so if I come back over to here, I just did the sine, which would be this part here. I'm going to do the cosine. Execute. Okay, so, and then just to verify that this is actually going to return a proper 40.0 degrees, let's try taking the inverse of that. So, I think it's going to be the A tan, is it? Yeah, it's just the A tan of my x divided by, or was that the wrong paste? Yeah, that was the wrong paste. Let's copy. And is that the right one? That's the right one. All right, so divide that by, I'm getting there slowly, edit, paste. What? Where did it go? And if I execute that, I get 40.0. So that's good. So now what happens if I am over here and I move up this far? And this is not going to account the dip. This is only going to account the change in the horizontal elevation. So I need to change this from, let's say, a 0.247 kilometers to 0.245. And then if I go up 2 meters, then my angle is, come on. I got to get a slightly better. Oh, come on. How many times do I have to do this? Let's try it this way. Paste. Oh, we'll get there. For some reason, it just decided to throw that in there. Okay, so we've got 39.12468 59s before it starts veering off. Yeah, that's going to be, we're talking what? What is that going to be actually? Uh, well, why don't we do it this way? If that's going to be minutes, if that's going to be degrees, let's go with, come on, 60 times. This thing is possessed. What the? 60 times 0.9 should not equal that number. Well, anyways, I suspect it's going to be thousands upon thousands of times smaller than the error rate of your average sextant, which means that it's all going to get lost in the wash. So the next thing that I was thinking of, and I was kind of thinking about this last night, was should I use the math libraries that are in Java, Java high precision double. So there are some high precision, I think it's big number, is it? And do I essentially create a high precision thing like this? If you want to see me do something like that, I was thinking of putting this on my second channel and go through the Discord thing and all of that stuff so that if anybody wanted to chat and watch me do this, yeah, it's big decimal right over here. So there is in Java, I don't know how far back it went, if it was Java 7 or it's at least in Java 8. When did they start putting this in? If anybody's interested in watching me basically recreate a calculator like this, go ahead and leave comments in the description or leave a comment and let me know what you think. It would be kind of interesting to. I've got a few other interesting ideas of how I could go about uh, creating something like this. I like the idea of having something that is interactive like this, and you could just use an online calculator like this. But I was also thinking of if you're in a field, for example, that requires an interactive calculator with really, really high precision. In Unix, there is the ability to use in scripts, for example, let's say you're automating something and you want to do lots of real-time calculations that are all automated. So you could do something like what is, and you could just pipe that into the command line utility and that'll just output things like that. So it would be kind of interesting to do something similar to that where you could have a mode that has a high precision command line friendly calculator, or let's say maybe you've generated a script that you want to have a whole bunch of calculations performed and output so that it could then be fed into something else. So that would be something else that I was thinking I could end up doing. So if that is something that would grab your attention, just leave a comment below and I will think about making a quick little project that does something like that using those high precision API calls and whatnot. So that was really it for today. I just wanted to do something really quick, and yeah, it would seem that that is on an order of magnitude far greater than the precision of a sextant, which would mean that it would be entirely irrelevant and that we would not be able to measure any difference in angle to the star based on our height. So that's going to be it for now. Thanks for watching.